In functional programming, a natural transformation is basically a function that converts one functor to another. But not all conversions are natural. In this video, we will learn about natural transformations and the rules they follow. Let's consider is-even function. It receives an integer and returns a boolean. We can leave this function into a functor like f. Now map of is-even receives f of integer and returns f of boolean. An example of such a functor is array. Our lifted is-even function now receives array of integer and returns array of boolean. What seems to be happening here is that we are keeping the container fixed and changing what it holds. What if we do this the other way around? What if we keep the inside fixed and instead transform the container? For example, here we are transforming container F to container G. And this is the topic of this lesson. What is the best, cleanest way to define such transformation? Well, we kind of got the idea when we were simply spelling this out. We want to convert F to G. It means for any type like X, we want this transformation to hold. In other words, the most intuitive way to think about this is a good transformation doesn't care what these containers are holding. The transformation doesn't pick inside the containers when converting F to G. It only cares about outside. And this kind of transformation is called natural transformation. In order to understand this better, let's look at an example. Let's consider a function that receives an array of integer and returns an option of integer. Can you think of a useful implementation for this transformation? Let's consider a function that returns the first element of the array and let's call it head. When head receives a non-empty array, it returns some of the first value. And in case of an empty array, it returns none. Now let's swap the inner type with boolean. How about switching it with a type called pointer? What is pointer? It doesn't really matter. In case of an imaginary custom type like pointer, we are still returning the first element, which is p1. As a matter of fact, since array and option are both functors, we can map over them to switch between the types inside. As you can see, this leads to a diagram of function connections. Sometimes there may be multiple ways to convert one type to another. For example, consider array of integer and option of boolean in this diagram. How can we convert array of integer to option of boolean? We can either apply map of is-even first and then our transformation function, or we can apply head first and then map of is-even. This creates ambiguity. Which composition is the correct one? We solve this ambiguity by saying if head is a natural transformation, then these two compositions should lead to a same function. This rule guarantees that the head function is not checking what type containers hold and only reason on the containers themselves. This is natural transformation law, or simply naturality. Naturality states that a transformation between two functors is a natural transformation if for any morphism between x and y, the diagram above commutes, meaning no matter which route we take, the result is the same. And if that happens, we have a natural transformation. By the way, natural transformations are not unique to the pair of containers. We may have multiple natural transformations from array to option. To close this video, it's interesting to note that the idea of naturality was one of the motivations for creating category theory in the first place. The goal was to formalize the idea that whether you do the construction first or map first and then do the construction, you get the same result. In other words, a natural construction behaves consistently with the maps between the objects involved. And with that, thank you for watching this video. Please like and subscribe, and I will see you in the next one.